In example 3, work needed to lift a cable. A 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? Now here we don't have a formula for the force function, but we can use an argument similar to the one that led to definition 4. Now let's place the origin at the top of the building, and the x-axis is pointing downward as in figure 2. So here's 0 and it's pointing downward, and there's your cable. There's delta x. Okay, so we divide the cable into small parts with length delta x. And so if x subscript I is a point here in the ith such interval from 0 to 100, then all points in that interval are lifted by approximately the same amount, namely x subscript I. Now the cable weighs 2 pounds per foot, so the weight of the ith part is 2 times delta x. Thus the work done on the ith part in foot-pounds is the following. So we're going to take the force, which is 2 delta x, times the distance, which is x subscript I, which is equal to 2 times the distance x subscript I delta x. Now we get the total work done by adding all these approximations and letting the number of parts become large, so as delta x is approaching 0. Now using that definition, the work is equal to the limit as n approaches infinity of I is equal to 1 to n, 2 times x subscript I, which is a distance, delta x, which is equal to the lower limit of 0 to 200, 2x dx. Now taking the antiderivative, that gives us x squared going from 0 to 100, which is then equal to 10,000 foot-pounds. Now if we had placed the origin at the bottom of the cable and the x-axis was pointing upward, then we would have gotten the following. W again would have equaled the upper and lower limit from 0 to 100, but since we're going to take 100 minus x would then be the distance times the force, which would be 2 dx, and it would give you the same answer.